There's more value in the connections outside of these talks than actually listening to the talks themselves. Like we've spoken to a lot of very experienced, very tenured people who have lots of, great stories and mistakes that we can learn from so that we don't have to make them as well.
Good morning. Welcome to a session that looks a little bit into the hardware side of the world. So that's a gentle introduction to software engineers about the hardware. Me, Ignas Bagdonas, and I will be trying to show you a little bit of what happens beneath. But before we go to that, one kind of my happy administrative notice from kind of pleasing me as a speaker. I came here 10 seconds later to the room than the first attendee, and that's Mariam over there. So she gets a virtual prize. Thank you for being so much interested in my talk. Then let's, as this is first session in the morning, start from a question. Where does C++ run? What do you think? Well, you write the code, compiler does the magic, and what happens? Yeah. Pardon?
On the abstract machine?
Yes, it runs on the abstract machine. That's correct. Have you seen one?
That's abstract. It runs on the CPU core.
So the word is that abstract machine is quite rare, although in the universe there are quite many of the rare species. One of them is a spherical cow. But here you see a picture of a spherical cow in a vacuum, right? So that apparently is more real than the abstract C++ machine. So if we try to look more from the practical perspective, C++ actually runs on the computer platform, on a mix of hardware and surrounding components. So what's that platform? We are oversimplifying the things here. So that's a processor and that's a memory. There's something in between that allows for them to communicate. Well, and the rest of the world is the I/O side, which is important, but we don't care about that in the context of this talk. Long time ago, processors looked like that. That's actually the part in the center is a processor. With time, they shrank a little bit. Memory initially was made of inductors, then it moved into capacitors. Then there was an interconnector. Long time ago, I remember soldering one myself, similar to that. So here's a processor, here's the memory, and the rest is something that we don't care too much. If we fast forward 40 years until now, processor still looks like that. It has slightly few more pins, like a few more thousand. Memory also has increased a little bit in various properties and capacities, and the interconnect, well, that's really scary, but we don't care about that in the context of this talk, therefore we skip it. So let's start from memory. In essence, memory, dynamic memory, the entity that you are using to store your code and data is an array of capacitors. The element that stores the actual logical level there at the lowest level is a capacitor. Capacitor contains a charge. That capacitor is controlled. It can be switched on into the fabric, which allows for that value to be read, to be written, and a myriad of those capacitors eventually forms the memory module which you are using. How does that work? There's a protocol defined for sending out operations and retrieving back the data into the memory. And here we are talking about the protocol in the electrical domain. That means we send in some signals, we have timing parameters, and after some time we get a response. How does a memory interaction look like? A note about the addresses and other parameters here. We are not talking about the software visible addresses here. That's something very different. We'll come to that in the course of this presentation. So imagine we have our hypothetical memory array. We send a command for addressing the portion, the horizontal portion of that array. That's called activation. And we wait a hypothetical nanosecond for that to take effect, so basically sending it in. Memory array and the logic that does the work internally, we have to wait. Then we send another portion of the address coordinate. It selects a fragment of the previously selected row. Then again, we have to wait until all of that happens internally. Only then we actually get access to our data that's contained at the addresses indicated. Then, after we have finished reading or writing, especially reading, the structure of the dynamic memory is such that any operation is destructive. Therefore, if we read something, we actually destroy the value that we have read. Therefore, we need to return it back. That's called pre-charge. Also, memory by itself, and that's basically due to the physical nature, it cannot hold the charge all the time. You need to constantly reread and rewrite that. That's called refresh. That has to happen on the order of tens of milliseconds for each and every addressable entity. Then you ask for that to be pre-charged, and then you wait again. If you look into all this timing diagram, well, yes, we are talking about nanoseconds, but as somebody here in the audience has on its badge, nanoseconds matter. Right, nanoseconds add up, and you get quite noticeable seconds overall that's visible in your performance. And the problem here is that actual data transfer, or the useful goodput of the memory interface is roughly 10% of what it is possible from a theoretical point of view. Why? There are laws of physics. If you want to charge or discharge a capacitor, well, it has a charge, that's voltage. You need, if you want to discharge it, you attach it to some resistance, there's current flowing. Right? The larger the current, the faster the capacitor will discharge. The problem is that if you start talking about a kiloamperes there, this is inside of a really small integrated circuit, and there are lots and lots of other such capacitor cells around. You cannot talk about large currents. If you want to charge the capacitor faster, well, that's simple. Apply higher voltage. Again, that is controlled by the transistor, the switch, right, which has its isolation barrier limit of what voltage you can apply to that. So physical properties govern what you can have performance-wise. Now, marketeers certainly would be happy to sell you another generation of memory which is an order of magnitude faster. If you compare, in real-world examples, DDR1, which is 25 years ago, and DDR5, which is today, the actual capacity array speed is the same. Like 200 megahertz for one and the other. Back 25 years ago, DDR1 at 200 megahertz capacitor array speed was top of the line. For DDR5 today, that's, well, ultra budget. But still, the actual speed of the capacitor array hasn't changed that much. What has increased substantial in many orders of magnitude is the green part in this diagram that we don't care too much. Well, we care, but it is irrelevant to us. The actual speed of transfer of the data has increased. Yes, you can transfer a whole lot of gigabytes per nanosecond. The problem is that you cannot source those from an array, and you cannot sync them into the array. So what shall we do? Well, first let's look a little bit from a theoretical point of view. Why do we have these specifics in memory? It's hierarchically or two-dimensionally addressed structure. Again, that's done for electrical engineering type of reasons, that you cannot have everything aligned in one row and be free from signal integrity problems. There's also deep aspects related to the manufacturing process and so, well, scary analog electronic stuff. From the protocol perspective, you also have a limited amount of signal pins coming in both into the module and into the actual memory component. And that is one of the limitations why you need to have the dynamical structure. Then you also need to remember that memory is dynamic. The dynamic memory is dynamic. Well, it shouldn't come as a surprise. It holds the actual state, the charge, only for a rather short amount of time. If it's not touched, if it's not read or refreshed, it will that value will get lost. The way how the external entities from a context of a memory is actually the processor that is dealing with the memory. Those are two separate worlds, starting from addressability. The addresses that the processor core deals are very different than the addresses an actual memory module deals. There are multiple layers of translations. You might be familiar with physical to logical translation on the software side. Yes, that's happening in the core, but from a memory perspective, that's what is called the geometrical addresses, where linear physical address space, as seen from the processing socket, not the core, the Uncore part, is actually fragmented and distributed to different memory modules, both internally and externally. And the reason for that, if we look again back into this our diagram, we have spent roughly 10% of the good put for doing the actual work. The rest of the time we are waiting. That means that the signaling bus is actually free. That means if we have an ability to send additional commands which talk to other addressable entities in memory array, we potentially can gain some benefit by utilizing that bandwidth in a more practical way. So let's look into how that works. Memory is partitioned logically into entities called banks. So this diagram that we have here basically illustrated what is happening inside of the bank. One bank can have one one addressable element open at a time, regardless of its size. Therefore, if we want to increase the actual good put, we partition the memory array into banks. Historically, it came with DDR1, DDR2 transition. Then it was discovered that this is a good idea. Then we have another layer of indirection on top of that, bank groups, because previously too few bits were allocated for addressing. Well, 4 banks should be enough for everyone, apparently not. Then we have bank groups. Then with time, it came to realization that there are basically properties from purely electrical domain. You cannot have an integrated circuit and a memory chip of that large capacity. Therefore, on a memory module board, you would solder twice the elements. Therefore, you need to address those two. Those are ranks, multiple of them. And if you look at a contemporary memory module today, that is something that can have multiple pages or rows open. Again, within one addressable bank group, you can have one row open to which you can send read and write commands. Depends, the actual absolute numbers depend on the specific layout of the component, how many ICs are soldered on that, what's the capacity, what's the geometry of those. We can talk about, say, 32, 64, up to like 256 banks on the module. That means if we remember back our transfer diagram, technically there can be tens or up to low order hundreds of pages open for which we can actually send and receive data. So in theory, yes, there is a possibility to actually use the memory bandwidth, the physical memory bandwidth, up to some practical limit. The problem is that throughput or bandwidth is not the only important aspect. It's also latency. And the fact that you have more banks open at the same time doesn't directly influence or decrease the latency. So the latency is still the same. Moreover, if we increase the transfer speed, but remembering that our capacitor array still operates at the same frequency, actually the latency increases. So if you look into absolute terms, for many practical use cases, the newer generation, like DDR1, is actually faster than DDR4. For micro benchmarks, the picture will be very different. Yes, it's certainly possible to craft a micro benchmark which will show you that everything runs just perfect. However, for practical users, memory is not getting that much faster. The absolute increase generation to generation is not that good. Therefore, it is getting wider in the sense that you might have more operations outstanding. That's an important aspect from a software perspective. How do you design the things? Some talking points about mostly kind of trying to clarify some marketing aspects. So HBM, yes, that's a next generation thing that will solve the bandwidth problem because it has 1 kilobit of bus width. In reality, it doesn't. That's actually 8 separate channels, and if you want to utilize them, you need to send out 8 separate commands. What does that mean? If you have one processing core, you need to do 8 times the work. Yes, that will help if you have multiple parallel cores, say like in GPU or some other parallel environment, and that it is targeted for that. However, the fact that something is wider does not necessarily mean that you will be able to use that basically by recompiling the things. The important aspect here is to understand the mapping of the addresses. We'll come to that a little bit later from a perspective of a processor core too. So what's important to realize that the same memory capacity can be realized very differently. And this is from a theoretical point of view. That's what the standard specification says. Vendors sometimes interpret that even to a more broad extent. Right? The same capacity can be arranged by very different type of memory modules. What does that mean? The row size, or what is called the page size here on the last line of the table, it's different. Therefore, from your software perspective, your page size is typically 4 kilobytes. Depending on what particular memory type you have in your system, that will access 2, 4, or 8 different pages. How those pages get mapped to the actual memory module, to which physical slot, to which rank within physical slot, to which bank group, and so on, that depends on low-level software, basically the boot environment that sets those things up. You generally don't have control to that. Moreover, you typically don't even have access to information of how that is how that needs to be done. That's strictly guarded by a ton of NDAs from a vendor perspective. Therefore, it's an important aspect. And if you care about the performance, you should care about what's the actual memory geometry in your system. And if you really care about the last nanosecond, you will actually lay out your data structures in a different way, depending on what physical memory is in your machine. Or the other way around, you will basically restrict your code to run only on a particular memory topology. Now, the memory in the global context. The memory is basically interacting with the cores and uncores. So the core is something that runs your code. Uncore is something that sits around it and provides a last level cache, the I/O interface, interconnect between the sockets, and sometimes from complexity of what it is doing, sometimes that's even more complex than inside of the core. The cores are the clients. They send in requests to the memory. Memory does the work. Requests come in. That does not necessarily happen in order, and for most practical cases, that will happen out of order. Remember our diagram about the latency. If you have multiple requests coming from your core for reading particular locations, waiting until you get serviced for the first one without not issuing the next one, that would be a loss. However, you can have only one request for an open page, and therefore the memory scheduler needs to look into the aspects of whether to delay this particular request, waiting in future speculatively that there will be another request coming in for the open page, because that will be noticeably higher from a performance perspective. Or close the page, open a new one, and realize that the next coming memory request once again wants to speak to the previous page. And this is the source of a complexity what the memory controller does. That sits below the software level. This is purely on the hardware side. Yes, it's controllable from a software side, but that's something that's implemented on the time scale way lower than the granularity what the software can do. There's also caching. You certainly are very happy from the software perspective that what you do in one thread magically gets visible in the other thread, even if those threads happen to be run on cores on the different sockets. But in order for that to be implemented, there's a complex and expensive mechanism of signaling going back and forth that allows you to do that. One of the limiting aspects in the scalability of the memory system performance is actually synchronization of the caching. Therefore, if you care about the nanoseconds, have less sockets in your system. Each additional physical socket makes the overall system more complex, and in absolute timing for synchronizing the memory, that's a loss. That much about memory. Let's look at the other part of the equation, the processor core. That's really simple. You feed instructions from one side, you allow access to the data, and it just does the job. Simple as that. What can be more complex? Well, let's look into what the processor core does internally. So first, in order to do something meaningful, you need to get the instructions. Right? That's instruction fetching. Typically, it goes not byte by byte, but on a cache line or sub-cache line granularity. There is a difference whether you are executing a linear piece of code or you are incoming from the branch, from somewhere else. Depending on the actual implementation details, you will be able to read more or less instructions from that. Then once you know what to fetch, that is simple. However, you have branches in your code, and branches are one of the sources of the complexity. If you want to run fast, you better run ahead. Therefore, you start reading or fetching the instructions that you think you will be executing at some point in time. If you have a branch, well, you have two options. You have a flip a coin, take one or take the other. Flipping a coin might be a good strategy, but we can do something better. That's branch prediction. Depending on many of the aspects, whether we have seen that branch, what's the previous outcome, and so on, we may have basically influence decision whether we should follow that path or not. So branch predictor, that's the entity that influences what code will be fetched next. Once we fetch the things, we need to decode. And here's an important aspect. The code that you read in the compiler output is not what the actual core executes. That's just a contract. You say that, well, I want to move from this register to that register, or I need to add to this register 27, or I need to load that particular value into that particular address. That's the intent. You are telling what you want to do. However, what's happening inside of the machine, that gets translated into the internal representations. For most of the instructions, mapping to instruction to operation is one-to-one. However, there's a difference if the platform, for example, x86 is a memory register machine. The same instruction may access the register, and the exactly same syntactic, basically semantic instruction can access the memory. The difference is in the encoding. From the functionality point of view, those are very different operations that are happening inside. If you're accessing the register, well, that's rather simple. If you're accessing memory, you need to do several things prior to that. First, you need to generate the address for memory. Second, you need to send out a request for reading that. And only third one, you implement the instruction. So it might be that the instruction that looks like a single element from the code perspective, inside actually decodes into multiple different entities, and that's what happens inside the machine. You might have heard especially from a marketing perspective, the width, and vendors like to measure the width amongst themselves a lot. My decoder is wider than yours. What does that mean? It's basically it's a limit of how many instructions can be fetched at the same time, how many of them can be decoded. Not all instructions are equal. Some are more equals than others, in the sense that they are more complex to decode. They might be microcoded, something like a subroutines. Then it's a question into how many of the operations that gets translated to. That's the width of how many actions to do you can feed into the machine. And there are some misconceptions, in particularly in the world of x86, which is a variable length machine, that you need to do this process serially. Because you don't know the instruction length in advance. Well, that is factually true. And you need to decode the instructions serially, sequentially. However, if we look into the hardware domain, hardware can be parallelized really easily, and that's not expensive. The way how that works, right? You fetch the block of your instructions, say 16 bytes. Then you take each and every byte, run 16 comparators, checking whether this particular byte is, for example, C3, which is a read instruction, right? Then run another comparator which checks whether that's a length-changing prefix. Run another comparator, whether that's some register encoding. And here you have a forest of different inputs that you feed into something like a priority encoder, which starts to correlate among the subsequent elements, subsequent bytes. And what you get at the output is basically an indication that, right, my instruction starts here, ends here, it's this class, it's this type, it has these modifiers, and it accesses those registers. Right. It might seem that this process is complex. It's complex size-wise. You need to have quite a lot of logic. It's not complex processing-wise. We are talking about a combinational logic here. For most cases, you don't need storage for that. Therefore, you can do a lot of this pre-processing in one single cycle. Therefore, take the fetch block, get the output. That's doable. It's a myth, widespread myth, that decoding x86 is expensive. So once the instructions get decoded, they get into the queue, not instructions, apologies, operations, waiting for to be executed. Now let's look into the other aspect of internals, the code density. Again, if we try to compare x86 to some others, the difference is that x86 is a variable length. So we already know that decoding that is quite simple. If we have a hypothetical example here, which simply assigns a 64-bit value to some particular variable, which happens to be in a register. In x86 world, that's just 10 bytes decoded into one micro operation in this particular case, and well, we are happy. If we look into some other alternative views of the world, so that's for MIPS, that's for famous RISC-V, right? That one requires 6 instructions for encoding exactly the same functionality. Why? Because the instruction length is fixed at 4 bytes. Regardless of how hard you try, you cannot squeeze in 64 bits as an immediate into 32-bit space. And some more bits even need to be reserved for indicating the actual operation. Therefore, what happens here, you split that operation logically into basically bit fiddling back and forth. You take the portion of the immediate, load it into the register, take another portion of the immediate, load it into another one, do logic operations, and so on. Well, Spark, that's another alternative, does exactly the same thing, just a few bits reversed back and forth. And that's ARM. ARM actually learned the lesson, understanding that, and to give a clarification, we are talking about the ARM64 here. Machine has 64-bit instructions. However, its 64-bit registers. However, its instructions are still 32-bit. That's by design, and that's not broken. That's the ideology of ARM. The cost that you have to pay here is that in order to load one particular 64-bit immediate, you have 4 instructions. Well, at least 4 is better than 6. Can this be tweaked somehow? What can we do? Well, if we add some more complexity into the decoder logic, it might be that it will recognize this pattern, say, okay, I have a sequence of instructions going one back to after the other, which access the same register, and they all have the same pattern. What does that mean? That means somebody wants to load a 64-bit immediate to the particular register. Fine, let's glue them together, and those four instructions will emit one operation, which will get into the execution. Where is this specified? Nowhere. This is not an ISA level contract. This is an implementation aspect. Therefore, if you look at ARM specification, if you look at the x86 specification, you won't find anything about that. That's purely implementation aspect. Some platforms will do that. Some platforms will do that better. Some platforms won't do that. And the reason why a particular instance of whether x86 or ARM or RISC-V or whatnot is fast or not fast depends on the aspects of how that is implemented internally. The externally visible ISA is a contract, nothing more. Basically, you feed the intent. The way how that is implemented, well, in hardware circles, there is a famous saying, if you want to run faster, you need to build faster hardware. Whether that is by implementing certain algorithms in a faster way, whether that's implementing certain alternate data structures which will provide you the answer faster, or whether that's eliminating the work that you have to do, it's your implementation decision. From the architectural point of view, nothing of that is specified, and that's the reason why we have multiple platforms, and in general, those platforms compete by the internal implementation details. Those details are not visible, and they should not be visible. You need to be aware of those, how to use that, in a sense, how not to get in the way of this. Now, in this particular ARM example, if the compiler stuffs in another instruction in the middle, which doesn't belong to the sequence, most likely the fusion will not work, right? And then you will have to execute that as 4 separate instructions translated to one operand, one operand instructions, operations internally. Then about the registers. The actual machine, the registers that you see in the compiler output are just, again, the contract. Internally, you have many times more, on the order of low hundreds of registers. The way how that works internally, they are simply being allocated as needed. We will have examples with that. The fact that, again, a popular myth that x86 has a shortage of registers. Well, on paper it does. However, in practice, it's just needed for signaling the actual instructions into the machine. What happens inside? You have plenty of those available, and this is where the out-of-order execution mechanism starts to be visible. You signal what you want to do, and you wait, and machine accumulates the state internally, and as the actual operands and the data dependencies become available, it executes that. Well, that's a question of a resource planning. Not all internal operations are equal. Not all execution units are free at the same time, and you need to balance what operation goes at what time. And finally, it goes to the execution. So starting from a very top where you read the instruction that you want to move this particular value, it finally came to the execution. Now, execution also updates the branching factual results. Therefore, everything that was happening here before the execution is speculative. Well, if we hypothetically say that each of those blue squares is one cycle, so you have to spend on the order of 10 cycles before you actually get to the execution. And this is coming in a pipeline. So at stage 1, you are decoding, then you are going forward, and the next fetch block is coming afterwards. And therefore, you have the stream of instructions in flight. Therefore, branching is important. If you make a branch prediction failure, you have to flush everything and forget. And then you finalize it, then bring externally observable behavior back into the order that it should be. Then we have interactions with memory, then we have the caching system, and then it comes to memory only. What precisely is out of order? Out of order not in the sense that it's broken, but what is being rearranged? Not that much, in fact, only the execution part. You have a lot of it, right? There's a lot of operations waiting in this queue, but that's, in fact, not too much of work. However, what is speculative? In the sense that you think that you're doing something, but that does not necessarily mean that this state will be externally observable, pretty much everything. This has an interesting consequence that if, for example, you make a failure in a branch, you just flush everything out and start from the beginning. Yes, you have paid the price of a few tens of cycles. However, you also have certain operations that interact with the external world. You can speculatively read memory. That means that something will be brought from actual memory into the cache. And you can speculatively read things that you are not supposed to read. That's the source of all meltdown, spectre, and other side channel attacks. Even if, say, operating system or memory protection would not allow you to access that particular memory, basically you run out of bounds, the hardware will happily allow you to do that. And in fact, it does it all the time. And only then at the execution phase, it will be realized that no, you in fact don't have permission to access that memory location. Therefore, the instructions will be thrown away. But the memory line that came into the cache, it will stay there. Therefore, the next time you try to access, again, speculatively, and if you measure the timing between those instructions, you might get a very strong side channel indication that this particular line is in the memory. If you add some more creativity, you can actually even find out the values in that block. And that's the reason, basically that's the mechanics behind those attacks. Therefore, if from a software side you think that everything can be reverted, in the physical world side, not necessarily everything can. Then the address spaces. So on the left side, this is something that you generally deal from the debugger side and runtime side. The actual hardware deals with addresses that are different, translated into the physical domain. That's where the paging and then memory protection comes in. And that's common for all the processors running in your machine. On the left side, each and every processor runs in an isolated space. Enough of the theory, let's look into practical examples. So the most important function. It checks whether the condition is 27. If it's yes, it does this. If not, it does that. So let's try and run. So first we run that with the wrong parameter. That's 42. This is actually an example of the code which gets generated. So let's see what our hypothetical core does. It fetches, the fetch width is 16 bytes. On operation, we get the block. It can decode 4 instructions per cycle, right? So we do the logic, we calculate the instructions, we see that there are 4 instructions, we throw away the remaining amount of what we have fetched and see what happens. So that's conditional, and the second one is a branch. We look up at the branch history table. This is the first time we run this function. Therefore, there is no entry in branch history. Now, but in particular in the x86 world, there is a notation that if the branch is going forward, it is not taken if we don't have any other data. If it is going back, it is assumed that it is taken. That's one of the reasons why your error handling code typically is allocated at the end of the function and loops branch back. Basically, the loop checking condition is at the end of the loop. What does that mean? We looked up a branch history table. We see no entry there. Therefore, this branch is not taken. Therefore, we fetch another block. It's unaligned. That will be more expensive to do. We take another 4 instructions, we decode those and throw away what we don't need. We see an unconditional branch in that next block. What does that mean? That this will be taken anytime regardless of any conditions. Therefore, whatever we decode afterwards, we throw it away because we will not be executing that. Fine, let's fetch another block. We get a couple of more instructions. And what will eventually get into the execution units after all the queues and all sorts of things, the wrong branch will be executed. And, well, how can this be? What are we doing here? It's not a problem. the conditional instruction will get executed, and we will see that it is actually wrong. Therefore, everything that we have done so far here will be thrown away and restarted from the point of the wrong branch. The branch will be updated, saying that this branch is taken, and everything will be refetched again and executed. Well, no big deal. We just wasted twice the amount of work, but eventually the result is correct. Let's rerun this example with another parameter. Now, it's exactly the same setup, the second call with the different parameter. Therefore, well, we fetch again, we get the code. This time we have branch history. And the branch history says, this branch is taken, therefore you go forward. The branch cannot know the condition. The condition will be evaluated only at the execute stage. That's something like plus 10 or 20 cycles ahead of where we are looking now. Therefore, we know the indication that this branch was taken. Therefore, we assume that it will be taken again. So therefore, we start fetching from where that branch is pointing. We decode another block portion of instructions. And we continue, we feed that into the execution pipeline, and then we realize that our branch is again incorrect. Well, we flush everything out and restart from the beginning. Branching today is the most expensive hardware-related performance aspect. Be friendly to your branch predictor, please. He will provide you with a lot of friendship. Some interesting developments in the contemporary hardware. We are starting to see the platforms that fetch from both branches at the same time. So that means that it will decode both the predicted and predicted not taken branches at the same time. From a hardware perspective, that's not too complex. Well, we have just two parallel decode units which do exactly same work. Therefore, we get two sets of instructions. Those will get fed into the execution. Some of them will be thrown away as wrongly speculated. Some of us will be executed. What we gain here, we gain in time that we don't need to restart the decoding process, decoding and all the subsequent steps from the beginning. Actually, what a smart compiler can do, and this is something like a recent Clang trunk did, it actually executed both branches. Without even involving the branch predictor here. Again, that's a question of the cost analysis. For this particular example, that's actually the correct strategy. You don't have branching here. You execute both of the branches, and the diagram, the data dependency diagram, illustrates that you can actually safely do that. From a performance-wise, you do twice as much of the work, but as you can do a lot of it in parallel, you have multiple execution units. This mostly comes for free. Let's talk about a favorite topic of Eduardo's, memory operations and strings and other things. Well, memcpy. Memory copy, well, you might think, why do we care about that? That's so trivial. Well, we read something when we write something out. However, if you look into the actual code, there's a lot of memcpy there. And the problematics there is that you cannot know in advance both the alignment and the relative alignment on source and destination and the size of the blocks that you will need to be copying. On the other hand, from a platform perspective, you have a multitude of possibilities here. You have a set of instructions on the scalar side. You have specific accelerators. You have vectorization. You have even off-core accelerators that are happy to move huge blocks of memory left and right. However, this somehow needs to be translated into the actual set of instructions. So let's look at what happens if we don't put too much effort and how that works. So a simple naive memcpy implementation, we check whether we have anything to copy, and then we copy. The resultant code shows that we have a loop and we copy that byte by byte. Again, that's the intent into the machine. It does not necessarily mean that internally it will do like that. It will probably realize at some point in time that you're trying to copy large amount of consecutive bytes. Therefore, it will switch into the larger units. Generally, you cannot know that outside of the context of a specific platform that you are doing. However, that doesn't look too, say, resource-wise. If we boost up that a little bit and we allow compiler to do some creativity, we get this. That's a large amount of code which actually does checking whether we have enough of work to do. If we have enough of work to do, then we move into the vector part. We copy at large chunks. However, this doesn't even touch the alignment question, so we assume worst case that both the source and destination and relatively one to each other, they are unaligned. Therefore, we use unaligned instructions, which may be more expensive. Again, depends on the platform. If we have little of things to do, we use the scalar way. Well, functionally wise, this works. The question is at what performance? If we add some creativity from our side, and that's actually the live example taken from ClickHouse, that's Memcpy Implementation. Right. And this results into this. The logic is pretty much the same. However, there are more checks, more conditions, thinking that it will be more performant. Now, also on top of that, they have allowed the compiler to do some creativity on top of its own. So it did some re-vectorization from SSC to AVX, did the cost analysis for that particular platform and thought that it will be better. This looks a little bit complex to me. What if we try and gently ask our underlying platform for help? With time, processor vendors realized that memory copy is really frequent operation. And the important aspect here is that the machine has the state of the context of where that memory copy operation will be executing. It understands the alignment, it understands the capabilities that the platform has got. And it can be programmed internally. So basically think of it as a subroutine. From a software perspective, well, it's just only 2 bytes. You signal the intent that you want to do enhanced rep moves for strings. Right? Inside the decoder, we'll see that, okay, well, somebody wants to do a memcpy, so I will branch to the microcode, which will feed kind of a predefined subroutine, which will do the checks internally. What size, what alignment, make a decision what internally best operations to use best, and will actually do the thing. Does that mean that this is the best option? You need to test that. And anything that is being discussed here in this context, you need to test that. And again, the important aspect to remember if we're talking about the performance. In theory, there is not that much difference between theory and practice, as the saying is. Therefore, micro benchmarks, they certainly might be fun. However, in practice, there is a huge difference between real-world benchmarks and micro benchmarks. If you, for example, do a benchmarking of this particular fragment that is here, you might get the results that might have absolutely no relevance to a real use case. Right? Don't get kind of trapped into that thinking. And in general, performance testing is complex. Now, another example. On Monday, Victor gave a talk about hashing. How do you deal with a hash table with a complex key? It was a nice example of how you write a friendly C++ code, and it comes down to the actual mechanics of how you calculate the digest. So that's Fowler-Nolvo function, nothing special, a few logical operations, you shuffle the bits back and forth, and that's it. Let's look at the impact into the performance. So first thing, we see 2 instructions which actually check for the loop condition. That's a candidate for fusion. Most probably the machine will notice that and will emit one micro operation into the queue. Then it will unroll the loop. From a software perspective, we don't have unrollment here. The hardware will do that on its own. It will simply copy that pattern, the inner body of the loop, and I have invented the fused instruction here. The CmpJNE doesn't exist in reality, but that's an indication that you have particular mnemonics for that microcoded instruction. Takes two arguments, compares those, if the condition then branches, if not, continues. Then machine will notice that we are doing separate iterations on different data. We signal that we use the same register, but that's only the intent. What actually will happen in the platform, for each and every of that loop iterations, it will allocate separate registers, physically separate registers. There's separate internal memory storage. Then what will happen next? It will realize that there is no dependency between those particular memory fetches and the actual users of the memory. Therefore, it will happily reorder that. What does that mean? Potentially, we will run out of bounds because we don't know whether the condition holds or not. We are executing memory loads prior than actually doing the checking and the loading. And that's absolutely normal. This happens all the time. So in a normal world, this would result in an exception. No, you cannot access that particular memory, or you will simply read random garbage if you're looking from a software perspective. From a hardware perspective, that's absolutely normal. So, well, out of band is your friend, because that gives performance. Now, if we look into the actual example that Victor was talking there, the key is composite for that hash table. That means that I have multiple elements which contribute to the digest. So that's key 1, 2, and 3. Now, we do a simple thing. We call that hash digest calculation function for each and every of the elements. This is a hypothetical example, so this is to illustrate how that works. And the actual function body is in a different translate unit. Therefore, the compiler doesn't know the implementation details. Therefore, what it does, it simply emits the calls. A call is a branch. So we will have 3 branches. Here, the first one most probably will be mispredicted because there's no previous entry. Subsequent ones very likely will be predicted as taken. Inside of the function that's on the lower right side, you also have conditionals. The first time taken, that most probably will be mispredicted because it points forward. Subsequent ones will be predicted likely correctly. If we translate that within the same unit, therefore, the compiler sees the internals of that and actually can combine everything into one place. We have a little bit fewer of branches here. Now, if we actually do the right thing, we need to rearrange our data structure. Instead of running 3 separate invocations of digest calculation on tiny elements, we rearrange them. Well, in this particular example, we actually pack them, which is equivalent to arrangement, and that's the whole resulting code. From a functionality perspective, that's the same result. From a performance perspective, that's a noticeably different result. Is that faster or slower? You need to test, and not in the micro benchmark environment, but in the actual use environment. Summarizing the talks about the performance. Performance is hard, and performance depends on a lot of low-level platform specifics. That is substantially below the level of what the software contract specifies, the instruction sets, and, say, visible observable behavior. The events and happenings, whether the branch has been predicted, taken correctly, incorrectly, how many instructions decoded, how many lines fetched, at what latency, and so on, all of that is visible. There's a large amount of specific platform-dependent counters. They are your friends. The only thing is that they are rather picky of whom they treat as friends. It's a complex area lacking substantial amount of documentation, and in general, this is very much platform specific. Generation from generation of the same hypothetical x86 machine, the amount and the internal structure of the counters will be very different. The other important aspect getting the actual performance counters is not free. Even enabling certain performance counters is also not free. Therefore, if you think that there is one magic line of code or magic library which you can link in, no, you cannot. This is a certain level of deep level exploration of what you can actually do with the platform. The platform is very willing to help you by exporting that information. However, in order to use the performance information, you need to do quite a lot, and sometimes the cost of getting the performance metrics out of the platform might be well more than the actual unit and the testing that you are trying to do. Does it mean that this is something that you should ignore? No, not at all. This is an important tool and very valuable tool if you care about the performance. Not an easy tool, so if you know the saying that C++ allows you to shoot into your feet easily, so all these hardware things that basically it's if you try to shoot your feet, it will ricochet and rip off your head immediately. Now, a controversial topic in the context of what we have been discussing here. It's a vision. It's not something that exists here today, but it might be that the industry is trying to look into that in a more serious and kind of coordinated way. ISA is a contract. Well, you feed instructions into the hardware and the hardware does something. And we have seen that hardware does a lot of internal transformation from one format into the other. Like a few decades ago, there was a huge heated battle whether RISC versus CISC which one is better and which one will rule the world. There's also a very long instruction word which sank together with Titanic. Now, if we look into the internals of the platforms, most of the currently relevant platforms have 32 registers internally. Yes, x86 is also getting that. EPX will be in a few generations, and that brings in yet another 16 general purpose registers, not vector ones, but general purpose. ARM and RISC-V, they all have that. The difference is between the load store and register memory logic. x86 is register memory, where you can have actual operation deal directly with memory. On the other ones, you actually have to first load memory into the register and then do the operations. There is a difference how you signal conditions. ARM has predicates, RISC-V doesn't, x86 has flags, but if we look from a functionality point of view, they do mostly the same. Well, they do equivalent thing in a different way. What if the external ISA is treated just as, say, front end of the contract, and the actual execution core inside, it's independent of that. Therefore, hypothetically, we might be talking about a machine which can accept x86, ARM, and RISC-V at the same time. What you need for that? Well, just 3 decoders, right? And then which feeds that. Again, I'm oversimplifying that you only need 3 decoders. You need way more than that, but that's from a conceptual point of view. That feeds into the actual execution pipeline. What's the benefit? In theory, well, there is a difference between the theory and practice, in theory and in practice. You might focus more on the actual execution side of the machine, the backside part, and treat the incoming instruction stream just as a contract, or maybe not. Right, I do have another part of the talk here about the vectorization, which is an interesting subject of my side, but we don't have time for that at this moment. Therefore, I will finish my spreading of a propaganda from my side, and I would like to invite for a discussion. Questions, comments, feedback, gifts, bribes, anything else.
I enjoyed your talk. Thank you. You were talking about the different ideologies of the hardware manufacturers and the taxonomy of the different types of processors. Recently, I got a new MacBook Pro and it has this Apple silicon in it. I was wondering if you could, if you know anything about where that falls in this taxonomy of processor types and instruction types, and what might have motivated Apple after such a long hiatus to develop their own CPUs?
So short answer, that's just ARM. ARM with some wrapping around. Internally, that's ARM 9.2, if I'm not mistaken, core. But that's just an ISA contract. The important aspect is what they implemented. And the fact that Apple Silicon, which is a marketing name, is performant is not because that it has ARM ISA. It's because that internally the design team knew what they're doing, and they did the performant implementation in the right way. That's it. Why it took so long? It's not an easy task. So Apple basically uses PA Semi intellectual property. They acquired the processor design house, and that was quite a while ago. And most probably, well, I certainly cannot claim, I don't work for Apple, but the general indication in the industry is that they have reused the internal engineering expertise that was gained at that time designing other cores. PA Semi was dealing with power derivatives and probably something else. But it's not that important what ISA you're using. It's important of how you implement that, right? That's the reason. They do interesting things. Like, for example, if you load a memory address, the core checks whether that looks like a memory address. And if it looks like a memory address, it simply issues a prefetch for that address. It's a speculative memory access, right? It might be that you are loading an offset, a pointer. Right? So if it senses that the value that comes into the register is a pointer, that might indicate that you will want to dereference that pointer. Therefore, it ahead of time issues a speculative read for that memory location to bring it into the cache. If your value looks like a pointer, but that's just a value, stream of bits, you have issued memory prefetch in vain. And that's one of the micro optimizations that might have impact. There's actually, if you're interested in those details, there's a really fascinating read of a few hundred pages of how Apple Silicon works internally. It's done by an enthusiast who reverse engineered that via micro benchmarks. I don't have the link right now in my memory, but I can find that for you. It's heavy reading, but that's eye-opening if you are interested about those things.
Hi, great talk, thank you. You mentioned that micro benchmarks are typically not representable of like the real use case.
Well, I didn't in particular say that, but let's assume.
Yeah, and you recommend to like run your code in the actual environment, but that oftentimes takes too much time. You're optimizing one small function, then you need to rebuild all your huge project, deploy, run some integration tests. Maybe you have some recommendations on like how to do more localized benchmarks. And I've seen some articles showing some tricks to free up the instruction cache, for example, before a benchmark.
So you want to have a cake and eat it too, right? In general, there's no one single answer that I can give you without knowing the context of what you are trying to do. Micro benchmarks may provide you with some hints. Then you kind of add more of those, and from micro benchmarks, the benchmarks become into mid benchmarks, then macro benchmarks, then the uber macro benchmarks, right? And you try to see the dynamics of what is changing there. Again, let's look from a practical point of view. It's not that often that the value of a micro benchmark is indeed that much valuable. You are looking at that as a fragment into the larger perspective of performance measurement. Therefore, it will provide you some indication of what's the possible impact. However, if you merge two micro benchmarks, for example, they may cancel each other. Right? You also need to look into those things. So if I may say something from my personal experience, is that you better have more micro benchmarks than less. Spread those around and do something like basically product of those? Well, it takes time, yes, but this allows you to get some kind of outliers or indications that are standing out of what you are expecting. Then you analyze those. About benchmarking on the real world data, you should do that if you can. And it's also not about benchmarking. It's relevant and correct about a lot of other aspects, right? Take, for example, profile guided optimizations and things like that. You run something on one set of data. When you rerun that in production on a different set of data, what data you get? Well, basically, what feedback you get out of that, and how relevant is this, right? So to summarize, there's no one specific answer that I can give you. This is an exploratory process. With experience, you start to notice certain things. Okay, this looks suspicious. Maybe I shall do that. But it's a form of creativity.
Thank you.
All right. All right, so we are what? Only 5 minutes over time. Good. So thank you for attending.